Alright, don't know what happened on the last video, guess it ran out of time, but let's pick up where we left off. We should have been trying to figure out the apothem and the perimeter to be able to figure out the area of a regular polygon, this hexagon here, using 1/2 apothem times perimeter. So we needed the apothem and the perimeter. We are working on the apothem. We use this triangle over here, knowing that if the sides are 16, the apothem cuts it in half. This leg of the triangle down here is 8. We started Pythagorean theorem to solve for the length of the apothem. When you plug this one in your calculator, you do get 13.9 is what we should have come up with. All right. Now that we know that, this is approximately equal because I did round that. So the next one is the perimeter. This part is actually really easy because we are given one of the sides, and on a regular polygon, all of the sides are exactly the same. So for the perimeter, that's just going to equal 16 times 6 for the 6 sides to get the total perimeter. So if one of the sides is 16 and the entire hexagon has 6 sides, we just multiply it by 6 to figure out that the perimeter is going to be 96. Once we know the apothem and the perimeter, we can plug both of those into the formula. The apothem that we came up with was about 13.9. And the perimeter we came up with was 96. We type all of those in our calculator. We do end up getting, you can type it in the Desmos calculator we were using earlier, you get approximately 667.2. So once again, approximately equal 667.2. For area, we always use square inches. It should already be labeled for you up there. So 667.2. All right. On question 12, this is a very similar problem. Only difference is it's an actual octagon, not just a made-up diagram of one. This is on the ceiling of a building. It says regular octagon in the ceiling of this cathedral has a radius of 10.5. So this piece here should be labeled already as 10.5. Remember, the radius goes to from the center of this polygon to one of the vertices. So that is the radius. The perimeter is 64. We don't need to label anything on the octagon. We can just put that we know the perimeter is 64 feet. All right, so find the apothem first. Obviously, that's important. See if we can't figure that one out. And then once we know the apothem and the perimeter, then we can plug it into the formula and find the area for this one. Apothem and perimeter. So first step, we already know the perimeter. Once we figure out the apothem, we can plug both of those in and get the area. So let's start with the apothem. Looks like we have this right triangle here, where we know the hypotenuse is the octagon radius that we were given, which is 10.5 feet. And we don't know anything else about this triangle yet. We do need to solve for the apothem eventually. And we could do that in a couple of ways. If we happen to have two sides, we could use Pythagorean theorem. Or if we know some angle measures, we might be able to use trigonometry. On this one, the only other information it gives us is the perimeter. conveniently, this is an octagon, so if the perimeter equals 64 and each side on this regular polygon is equal, I can figure out how much one of the sides is. One of the sides times 8. So if I divide the perimeter by 8, equals one of the sides, so each side equals 8 feet. So that means this entire side right here is 8. The apothem cuts that in half, so this little tiny leg on our right triangle over here is going to be 4. So we should be able to label that this leg is 4. Now we know the hypotenuse of one of the legs. We can solve for the other leg, the apothem that we're looking for using Pythagorean theorem. So A is one of the legs. We can leave it as A squared plus B squared equals C squared. A can stay the same. That's what we'll solve for. B is the other leg. And C is the hypotenuse. To solve for A, I can subtract 16 or 4 squared from both sides. Take the square root of both sides. Four squared is 16, that's where that came from. So whatever 10.5 minus 16 is, I'm pretty sure that ends up being about 9.7. So the apothem is approximately 9.7 feet. So we now know that the apothem is approximately 9.7 feet. Not sure what happened here, so 9.7 feet is what we end up getting for the apothem. All right. Now that we know the apothem and the perimeter, we can go ahead and plug those in to this equation. The apothem we just came up with was 9.7. And the perimeter was given to us at 64. So type that in your calculator, 1/2 times 9.7 times 64. We end up getting 310.4 approximately. And square feet. All right, so last problem that we have for area of regular polygons. It's an interesting question. It says, which are true of this regular polygon? Check all that apply. Notice several other things. Perimeter, we would need to solve for the perimeter if we want to know if this is true or not. The angle measure, we'd need to know how to find some angle measures formed by the radius and the apothem, which would be that one. We need to know a way how to figure out the angles, which on slide 13 shows you how to do that. One of the sides, we need to be able to solve for a side. The radius of the side length are equal. Is this true? Are the side length and the radius equal? We'll see in just a moment. And then find the area. So we basically need to find the radius, the side, the area, and then compare to see what of these answers are actually true. All right, so let's start with the triangle that we have right here. Let's see if we can figure out an angle and use trigonometry to solve for any of the other two sides. So in this right triangle right here, I see that there is an angle created between the radius and the apothem that I should be able to figure out. Because this is a regular hexagon, that means that there are 6 of the exact same triangles. If you draw all of the radii, we come up with 1, 2, 3, 4, 5, 6 congruent triangles, which means around the center of this circle is 360 degrees divided by 6 congruent triangles. Each one of these triangles is taking the same amount of that 360 degrees. So 360 divided by 6. We should be able to figure out what each one of these big angles is right here. So let's figure out this entire angle right here by doing 360 divided by 6. So I know that this is 60 degrees. I'm going to go ahead and draw that triangle here. And I know that the entire thing is 60 degrees. When we connect the apothem down the middle, we actually cut that isosceles triangle exactly in half to create 2 congruent right triangles, which means this angle that gets cut in half should create 2 congruent 30-degree angles. So if I'm just looking at the right triangle now, I know that there is this 8 centimeter piece here that we know is 8 centimeters, a 30-degree angle. I should be able to use trigonometry to solve for the radius if I needed to, and one of the sides of this right triangle, which I could then double and get the entire side length of this one. So let's erase some of this here, see if I can use it again to make it a little bit cleaner. All right, I should be able to solve for, let's start with this side right here that we just drew the radius. How could I solve for this? Well, using trigonometry on right triangles, if you know 2 sides and an angle, or if you know an angle in one side, you can solve for another side, or if you know 2 sides, you can solve for an angle in a right triangle. We can actually solve for this side by using one of the sine, cosine, or tangent ratios. So to do trigonometry, we need to first choose which trigonometric ratio we'd use. So from this angle, 30 degrees, there are 3 sides. There's an opposite side, there's an adjacent side, and there's a hypotenuse. We are only going to use 2 of these. We're going to use the adjacent side and the hypotenuse. So I can start by writing down the trigonometric ratio. Sine of an angle, oops, sine is not the right one, cosine of an angle equals adjacent over hypotenuse. This is the cosine ratio we learned when we did the trigonometry section. So if I plug in the pieces I know the angle and I know the adjacent leg. So cosine of 30 degrees equals adjacent over hypotenuse. If you want to solve for the hypotenuse, we can multiply both sides by h. And then divide both sides by cosine of 30. All right, so if you plug this in your calculator, we should figure out the hypotenuse on that triangle, and that will be the radius of the hexagon. So let's go ahead and type that in our calculator. 8 divided by cosine of 30. So we get approximately 9.24 as our answer.